Good morning, everyone. This is our presentation for EET 3250 Network Analysis, review of Chapter 8, The Sinusoidal Steady State by Future Electricians. Instructor, Dr. Sandrin Mubenga. Our group Future Electricians features Mahdi Al-Musalim, EET, Hussein Alrez, EET, Michael Farrington, EET, David Marston, Major Unknown, Brock Perry, EET, Benjamin Summers, EET, and Garrett Whitlock, EET. Our group motto is, "Alone we can do so little, together we can do so much," by Helen Keller. The agenda for today is theory and concept, formulas, problems, possible questions, tips, links to resources, and any questions from the class or the instructor. The expected time for this review is 15 minutes with roughly a 5-minute Q&A allowed if necessary. Theory and concept. The steady state response of a stable, linear, time-invariant circuit or system excited by the sinusoid is also a sinusoid of the same frequency. If the sinusoidal excitation is specified, we automatically know the nature of any given steady state response in the circuit. Sinusoidal sources are particularly important because 1. Generation, transmission, consumption of electric energy occur under sinusoidal conditions. 2. It can be used to predict the behaviors of circuits with non-sinusoidal sources. Continued. An assumption that is made in this chapter: all transients in stable circuits have disappeared. Because of this, current and voltage in the circuit will be given this form. I of t equals I times sine of omega t plus theta. V of t equals V times sine of omega t plus phi. The phasor representations of I of t and V of t are I equals I times E of I theta equals I divided by theta. And V equals V times E of I times theta equals V divided by the number of thetas. Formulas, particularly symbols. These are symbols that you'll see later on as we continue through the formula section. B equals susceptance, G equals conductance, R equals resistance, X equals reactance, Y equals admittance, and Z equals impedance. Because of this, we will not continue repeating these over and over throughout the formulas and just refer to them as their symbol. Formulas for impedance and reactance. Impedance equals Z of J times omega equals R of omega plus J X of omega. Inductive reactance. X subscript L equals omega times L. Capacitive reactance. X subscript C equals -1 divided by omega times C. Impedance of reactance. Z equals J times X. Formulas for admittance. Steady state admittance. Y of J of omega equals 1 divided by Z of J times omega. Admittance. Y of J omega equals G of omega plus JB of omega. There are more formulas throughout the section, and we encourage you to check them out throughout Chapter 8 to prepare for the final, but these are some of the most important ones that we found. Example 1. Using phasor methods. Solve for the steady state I of t, V subscript R of t, V subscript L of t, and V subscript C of t. And this is the figure that we will use. Z equals R plus J of X. Z subscript L equals omega times L, which equals 5 times 2 times 4 equals 12 equals J of 12. X subscript C equals -1 divided by omega times C equals -1 divided by 5 times 0.01, which comes out to -20 ohms. equals Z subscript C negative J 20. Z of R equals 6 ohms. Since all impedances is in series, the equivalent Z equals Z of L plus Z subscript C plus Z subscript R. The Z equivalent is shown below, comes out to 10 angle negative 53.13 degrees. I equals V divided by Z equivalent that we have just found equals 20 angle 0 divided by 10 angle negative 53.13, our previous answer, equals 2 angle of 0 minus a negative 53.13, which a negative times negative is a positive, which comes out to 2 angle 53.13 degrees. I equals V divided by our Z equivalent, which comes out to 2 angle 53.13 degrees. V subscript L equals J of 12 times I, which we can see comes out to equal 24 angle 143.13 degrees. V subscript L of T comes out to equal 24 sine of 5T plus 143.13 degrees. V of C equals negative J 20 times I, which comes out to 40 angle negative 36.87 degrees, which means that our V subscript C of T comes out to a grand total of 40 sine 5T minus 36.87 degrees. Next up is V subscript R, which is 6 times 2 angle 53.13 degrees, which comes out to easily 12 angle 53.13 degrees. From this, we find that V subscript R of T equals 12 sine of 5T plus 53.13 degrees. Example 2. At the terminals of a certain passive circuit, the net admittance in Siemens at a specific frequency is Y equals 35 plus J 120. A. Identify the conductance and susceptance. B. Construct an equivalent circuit for the admittance at the given frequency. C. Determine Z and identify the resistance and reactance. D. Draw an equivalent circuit for the impedance. A. Y equals 35 plus J 120, which means, using our formula shown earlier, that G will equal 35 and B equals J 120, which you can easily see where that comes from the given Y. B, here's a circuit that we have where the resistor is 35S and the capacitor is J 120. C, Z equals 1 divided by Y, which I'm going to go ahead and skip past all of this work right here and just come out to the answer for the sake of time, which equals 0.00224 minus J 0.00768. The R equals 2.24 milliohm. X equals 7.68 milliohm. Through all this work, we get a grand total of 15,625. And D, this is our equivalent circuit with the resistor and the capacitor in series. Example 3. Consider the RC circuit below. Assuming that the circuit is initially relaxed, determine the S-domain model and use it to determine the complete time domain current, I of t, and voltage, V of t. As you can see in our circuit, we have our source, the direction of our current, I of t, our resistor, and our capacitor. For the circuit, the Z equivalent will equal Z of R plus Z subscript C, which equals 3 plus our 12 divided by S, which equals 3 times S plus 4 and all of that divided by S. Our I of S equals V divided by our Z equivalent, which we found above, which equals 30S divided by S plus 4, and multiplying that by S squared plus 9. V subscript C of S equals Z subscript C times I of S. And using what we found so far, we get a total of 360 divided by S plus 4 multiplied by S squared plus 9. Using the trig formula from section 5.7, we can solve that I of S equals 4.8 after a lot of work, and our M subscript 1 of angle theta equals 18 angle 53.13 degrees. This helps us find our I subscript t, or rather I of t, which equals negative 4.8 times e to the negative 4t, summed with 6 sine of 3t plus 53.13 degrees. V of S equals a subscript 2 divided by S plus 4 plus R of S. A2 will come out to equal 14.4. M subscript 2 of angle theta comes all the way out to 72 angle negative 36.87 degrees. Using this information, we can find V of t, which equals 14.4 e to the negative 4t plus 24 sine of 3t minus 36.87 degrees. Now, the possible questions. Question number 1. Use phasor technologies, or rather techniques, to solve for steady state voltages and currents for a given circuit. 1. Redraw the circuit in phasor domain, where 2. Phasors transform all known V of t and I of t. 3. Represent unknown voltages and currents with V and I. 4. Replace component values with impedance, or Z, as we learned earlier, values. 5. Use any circuit analysis method or methods to write equations and solve them with a calculator. 6. Inverse transform the result, which is a phasor, all the way back to the time domain. Possible question number 2. Determine and plot the amplitude response and phase response for a given circuit. The slope is always 0 decibels at omega equals 0. If there are 1 0 and pole, slope changes by plus 20 decibels per second at a 0 and negative 20 decibels per second at a pole. If 2 zeros at the same critical frequency changes the slope by plus 40 decibels per second, 2 poles by negative 40 decibels per decade, and so forth. Start drawing a graph by drawing the frequency axis and labeling the first decade at least 1 divided by 10 of the first critical frequency. If there are no poles or zeros at omega equals 0, then enter the graph with a horizontal line, slope equals 0, on one of the amplitude axis. Continue that slope until the next critical frequency is reached. Add the slope change caused by the second critical frequency to the slope from the first. The sum of the initial slope plus the slope change is the slope used exiting the second critical point. Continue until all critical points have been reached. Possible question number 3. The steady state voltage across the capacitor blanks the current through it by 90 degrees. Here's a hint. We're looking for either leads or lags. Do you know what it is? The answer would be lags. Tips. If A of W is greater than 1, output phasor larger than input phasor equals amplification. If A of W is less than 1, output phasor smaller than the input phasor equals attenuation. The phase is always 0 degrees at omega equals 0. Capacitor phase angle equals negative 90 degrees. Inductor phase angle equals 90 degrees. In Laplace transform circuit analysis, all voltages and currents were replaced by their transforms. In steady-state AC circuit analysis, sinusoidal voltages and currents are replaced by phasors. The following are 2 links to some YouTube videos that we found very helpful while working on all the information that we put throughout this presentation, and we encourage you guys to check them out as well. Questions. So we covered a lot there. Do you guys have any questions? Let us know and we'll be sure to respond. References. Of course, we used the Thomas Floyd Digital Fundamentals textbook to help us do a lot of this work, as we have throughout the rest of the semester. Thank you guys very much, and if you have any questions, we will be in the chat during this class. So ask ahead.